Hello, I've decided to do a screen capture today. The written tutorials with all the screenshots and the text and the lengthy explanations are just as tedious to make as they are to read and to understand, so I thought this would just be easier on everyone. Just to pull it up on my screen, you can just see the changes that I've made and how to use them. So if you open up the GUI, the first thing you'll notice is that I added this panel, this Edge Bulks Effects panel. And we'll start with the dependents, and where it's a drop-down menu, and the thing selected right now is neighbors. And the reason it's called dependents is because that is what the weighting of this expansion efficiency depends on. So each particle has a set number of neighbors, and depending on the number of neighbors each particle has, the higher or lower it is weighted. So if we can imagine a scenario where we have lots of edge particles and lots of bulk particles, the edge-most particles will have fewer neighbors than the bulk-most particles, and the expansion efficiency will reflect that. And we can choose which one we want to weight towards. We can weight towards the edge, or we can weight towards the bulk. And so if we weight towards the bulk, what that would mean is that the bulk materials, well, right now the expansion efficiency is set at 100%, but let's say we set it at 50%. So the bulk most materials will expand to 50% of this, of 100% expansion efficiency, or sort of an ideal or perfect expansion. That would be characteristic of the edge-most particles. However, if we want to reverse that, we can say that the edge-most particles only expand to 50% of the bulk-most particles. And this expansion is reflected in how we apply it to the distances and the resistances. So for now, I've just loaded in the rectangular FCC, which if you go into the load network, this will be the file chooser that you'll see. This is in the root directory. It comes in the zip file, and here are some pre-made networks that I've built a while ago. And click on rectangular FCC. This is the one that you're about to witness. So I've assigned a resistance. We're just going to see what it looks like beforehand. So we go into the 3D plot. I've added a few changes here as well. And I've added plot visuals, and the choice of color maps, we can do red, blue. This one's very patriotic. We can do jet. And these ones take a while, just because this, I believe, have close to 250 particles and 800 some odd connections. So that's all that's all cool. I'll change it to winter. Winter's my favorite. And that's what it looks like now. This is what we're used to. And what we can do is we can now view the connections as well. These will take a while to render. Terrific. That's what it looks like. Nothing new, nothing too special. So let's, if Matlab will let me, hop back into the main menu, and let's create some distances. So click on calculate particle distance, and quick recap is we have a particle radius and a particle effective radius, and the distance between particles from an edge to edge will be twice the difference of this effective and real particle radius. So in this case, that's 2. When we calculate it, applies it, we're all set. And let's keep this as is. So the dependence is still neighbors. From the middle and available space have not been implemented, but if we do decide to go down that route, those do exactly what they say they will do. And if we apply this 50% efficiency to the bulk, so the bulk-most particles will only expand to 50% of the edge-most particles, or the particles with the fewest number of neighbors. So let's apply to distances, and let's see what kind of changes that make. So hop back into the plot. Hotkey is Control E. And right now it's still showing the standard view. What we can do is go into the connection colors and change this to distance. Blah, 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 blah. This takes a while. Okay, excellent. So can't really see what's happening. All the particles are in the way, so I'm going to turn this relative particle size all the way down, turn up this line width just a little bit. And now let's wait a good 30 seconds for Matlab to catch up. In the meantime, I will kind of go over the things that I've added here. Oh, terrific. If we kind of spin around, we can see exactly what happened. So these green lines represent the highest distances, where these darker blue lines represent smaller distances, and the colors in between represent these intermediate distances. And these numbers are actually kind of getting in the way a little bit, so let's turn off those numbers. Those numbers are the resistances and not the distances, just because that's what I had selected. And now we get this very cool looking effect, and it's doing exactly what we want it to do, where the edgemost particles have this much higher expansion rate than the internal or the bulk particles. And I think that kind of sums up everything that was that we're hoping to accomplish here in this particular update or patch or whatever you want to call it. Now there's a bunch of different toys here. We can change the particle colors from height to voltage, which will have this color scheme, but given to the nodes, and it will be reflective of the absolute voltage. And these connection colors, right now we have set it to distance, but if you model the network, you can change it from resistance to voltage drop, and that's very cool. But right now we haven't done that yet, so we'll just leave it as is. Alright. So Matlab is being slow and will not let me orbit and spin around to view all sides of this, but this kind of gives you an idea of what's going on. So I'm going to hop back into the main menu, and we're going to model this network. So I'm going to reset everything, assign the resistance to 1. Now I'm going to model this network. Let's see how long that takes me. Typically it's been around 20 seconds. So once this network has been modeled, I'm going to then assign a distance, apply this weight effect to the distance, use some pre-exponential and beta factor to turn those changes in distances into a resistance, and see if how heavily that reflects in this baseline resistance across the entire network. So with this, I think this is a 3x3x5 or 5x5x10. No, it's a 5x4x10 kind of rectangular FCC packing system. The baseline resistance is 0.343 ohms if every connection is given a 1 ohm resistance. That wasn't the best way to do that. But just a quick example, if I change the expansion efficiency to 50, and let's make it 75. Let's keep it 50. And weight it to the bulk and apply it to the resistances. Bingo, and let's do it again. And the goal here is that if we create special types of structures or structures that we are seeing in the SEM images, that we'll be able to recreate this bimodal distribution of resistances, where it's either very, very high or very, very low, and we are able to explain some of these topological effects, or seemingly topological effects of these networks, where in this case, depending on how much edge particles versus bulk particles, it would explain these discrepancies in distribution that aren't there in the ideal model. Okay, so here with 50% expansion efficiency at the bulk, what we notice is that the resistance actually goes down. How does that make sense? Oh, right, because the resistance in the middle is actually being decreased as opposed to before. Okay, and I'm right at the 10-minute mark, so I'm going to close this down. And if you guys have any questions, please email me, shoot me a message, text me. You know how to get a hold. And thank you for listening.